So our next talk is by Vicki Nielsen, examining the effects of implementing data-driven uncertainty and cost estimation models. So Vicki is an operations research analyst within the Office of Chief Financial Officer at NASA headquarters. In this role, Vicki serves as OCFO's point of contact for cost and schedule analysis, research, and model development. In 2017, she was systems engineer on the GW CubeSat project sponsored by NASA's CubeSat launch initiative. From 2018 to 2020, she performed academic research for the Mission Design Lab at NASA Goddard and TMAX at Jet Propulsion Laboratory. She remains passionate, driving change and innovation within NASA's project planning, control, and cost estimating communities. Please welcome Vicki.
Hi, everybody. So I'm going to talk about some research that I've done on examining the effects of using data-driven uncertainty and cost estimating models. Okay, so first I'm going to talk about some current applications of correlation within cost estimating models at NASA. Sorry, I just want to. Yeah, can you hide that by any chance? Thanks.
The three dots and then hide.
Okay, thank you. All right, so currently NASA relies on a variety of probabilistic analysis methods to estimate life cycle costs of our various programs and projects. These can be produced for a number of reasons. Like one of those reasons can be, establishing a benchmark to basically monitor or verify a project's programmatic performance. Or that can be to request or inform NASA budget requests from Congress. So when we make these cost estimating models and these parametric models that we use to determine these costs, correlation assumptions are usually a key driver within the probabilistic analysis. And they often create, they're often the biggest driver for the total output or the point estimate of the cost model. But due to the uncertain nature of correlation between random variables, NASA has had difficulty quantifying the relationship between spacecraft subsystems before. And this has been addressed in the past by either one, selecting a blanket correlation matrix to address uncertainty within the model. That value is based on an old research paper from this man named Stephen Book, who determined that the value should be around 0.2 or 0.3. And this is good because it adds additional uncertainty within the model. However, it's a heuristic and it arbitrarily affects the model's probability distributions without having a really firm basis in statistical fact or the historical project data. This has also been addressed in the past by opting out of using any correlation matrix altogether. So that either means no correlation matrix or a correlation matrix with a blanket values of zeros. In this situation, the uncertainty from the model comes entirely from the variability that's inherent to the model's underlying probability distributions. So while both of these can be methods that we take, it is maybe not best practice to continue going this route, since these are either heuristics or ignoring the fact that there's additional uncertainty. So for the purposes of spacecraft development, understanding how correlation can add this uncertainty can be especially important when we have state-of-the-art missions that have very limited historical data. So this topic has been researched a number of times before. However, there is a very limited practical application of this research. So what we'll discuss here is an attempt to kind of take one of these methodologies and apply it into one of NASA's cost estimating models and see how it improves the performance of the estimation. It's not going to. Okay, thanks. Sorry, bear with me. Okay, so one hypothesized method of creating data-driven correlation matrices that can be used within our parametric cost models is a methodology known as the correlation of residuals methodology. The correlation of residuals methodology involves deriving correlation coefficients from the residuals of the regression equation for the cost estimating relationship, which is the CER. This hypothesized method is based on decades of previous research. And it was implemented for our purposes in NASA's project cost estimating capability, also known as PCEC, through a Latin Hypercube simulation. So I'm sure you all know a thing or two about this, but just an overview. What is correlation? It is a statistical measure of association between two variables. It measures how strongly the variables change with each other. And there are typically two main types, Pearson's correlation, which measures linearity of a relationship between two variables, and Spearman's correlation, which measures the rank between two variables. So for our purposes, we'll be focusing on Pearson correlation. And then an example of positive correlation is here, which when one variable increases, the other one increases as well. So a directly proportional relationship. Then negative correlation, where one variable increases, the other decreases, inversely proportional relationship, or no relationship at all. So there's no pattern visible on the graphs. So just to give a little overview about the previous research that led to this, correlation is inherent in the process of developing CERs. When regression is performed for parametric cost estimating models, most of the uncertainty can be explained by the functional correlation of the regression equation. A little definition of functional correlation is it's the correlation that results from the mathematical relationships between cost drivers and CERs, and it can be modeled by an equation. So in cases where functional correlation is present, it is usually handled without the correlation matrix or coefficients, since it's already inherent to the model. However, one study determined that there's additional unexplained uncertainty that remains in cost estimating models because each independent variable is correlated with the cost or the standard error of the model to some degree. So that correlation is the uncertainty that exists between the unused independent variables, and it's not included in that regression equation. So that was described by this paper as causal statistical correlation between the unused independent variables. And this is not inherent, and it can be modeled as a correlation matrix of all the independent variables. So that is what we're trying to imitate when we use a correlation matrix of 0.3. And for our purposes, we'll put that into our model in a correlation matrix that has the subsystems of the typical NASA WBS work breakdown structure. So the hypothesis basically is that the CER residuals can be used to determine the subsystem correlation matrix, and this can be implemented into the model through the causal statistical correlation can be implemented into the model through that correlation matrix. So we have basically correlation. All correlation is statistical. Correlation can either be purely statistical, where no causal relationship exists, or it can be causal. So there is a relationship that exists and something is causing A and B to covary. And causal correlation can be broken further down into functional correlation, where there is an equation that can explain the uncertainty, or the causal statistical correlation, where there is a relationship. It can't be defined using a specific equation. However, it can be modeled using this correlation the correlation matrix that we'll describe. So we're focusing on the causal statistical correlation. Why do we care? The statistical answer is that adding correlation coefficients into the model has the potential to drastically change the measures of variability that are inherent to the probability distribution. So the standard deviation, variance, skewness, max, min, without having a major effect on the measures of central tendency. So the mean, median, mode. So this means that, this can increase the range of possible options that come from the probability density function. And it can be a huge contributor in the amount of risk that is associated with the cost estimates that you create. Now, in simple terms, that basically means that this can decrease, adding correlation can influence the range, and this can decrease the probability of estimating an average cost, and it can increase the probability or risk of estimating a higher cost. So this is pretty important when it comes to management of NASA projects, because when we create our cost estimates, we want to have a more realistic picture of what the true solution space is for the possible events. So how is this applied? Basically, this was a correlation matrix was created and it was implemented into NASA's PCEC model. This was done by creating correlation coefficients for each spacecraft subsystem and support function. And then this created a matrix that is a 20 by 20 matrix of the 20 different spacecraft subsystems or support functions that are part of the typical NASA WBS. The resulting correlation matrix was implemented into PCEC as an uncertainty factor, influencing the model's pre-existing cost distributions, and that was done using an Excel add-in called Argo, which is free from Booz Allen Hamilton. The Latin Hypercube sampling function of Argo was used to simulate results for PCEC for 40 different missions. So this was done with the correlation of residuals methodology. It was also done as a sensitivity analysis with a correlation matrix of zeros, a correlation matrix of 0.3, and a correlation matrix of 1 values. So the benefits of using PCEC, I'll be quick here because not everybody here might have access to it, but it basically was, it's a parametric estimating technique that's very familiar to the average NASA cost estimator. The CER uncertainty calculation mode allows for Argo to easily implement the correlation matrix. Just for some context, PCEC uses student T distributions, so that's where we implemented most of our uncertainty. It's compatible with Argo and the Latin Hypercube functions. And then the PCEC library, it houses a database with generally complete subsystem data for 58 of NASA's near-Earth robotic missions. And this is frequently updated. It's normalized, it's standard, consistent, and it removes the need for any additional data collection on our part. So as you can see on the right over here, the functions listed in gray are the subsystems, and the ones that are listed in the blue boxes are the support functions. So that includes attitude control, the recurring cost, and then non-recurring cost, command and data handling, recurring cost, non-recurring cost, communications, non-recurring and recurring, and then power, propulsion, structures and mechanisms, and thermal control. All of those have recurring versus non-recurring costs. So this is basically just a quick disclaimer, like if you are using PCEC, you do have to change the calculation mode to CER uncertainty only in order for this methodology to work. But basically it creates this correlation matrix. So it's highlighted, obviously, it seems clear that the negatives would be the red, positives would be the more green. This has 190 unique subsystem correlation coefficient combinations where 120 of these values are positive and 70 are negative. The most positive is 0.62, which occurs with structures and mechanisms recurring cost and electrical power and distribution recurring cost. This is pretty intuitive because, the more structure or mechanisms that you have, the more power you will likely need to operate it. Now, it may be more interesting thing to look at is the most negative correlation, which is negative 0.47. And that occurs twice between communications recurring costs and mission operations and ground data systems development. And then also between command and data handling non-recurring costs and phase E mission operations and data analysis. So this might not necessarily be intuitive. If I were to try and rationalize this, I might say that the more effort and money that you put into communications and data handling early on, the less you need support and money for data systems and phase E mission operations. But it really is out of our scope to figure out the actual causal reason for why that's happening. But it's important to note that not all of these coefficients might be intuitive to you. So Once we ran our simulation, I created some cumulative distribution functions for each of the different correlation matrices to show how the range of possible events differs. Basically, the blanket correlation matrix of ones produced the CDF with the widest range. So that's the yellow line over here. That makes sense because that is the version of this correlation matrix that's implementing the most uncertainty within the model. The blanket correlation matrix of zeros produced the CDF with the smallest range. That makes sense because we're implementing the least amount of uncertainty. And then the correlation of residuals matrix CDF falls between 0 and 0.3. And that is likely because it has a more nuanced fit on the data. So it doesn't necessarily shift all of both the tails out, but it creates a little bit more of a nuanced fit between the 0 correlation matrix and the 0.3. So that was just, that doesn't tell us much about the effectiveness of the model, but it just shows us how the range of the solution space increases or decreases. To look at the performance of the model, we created calibration charts, which is a technique of visually representing bias that's present within a model's predictive capability. Bias is the tendency of a statistic to over or underestimate the population parameter that's being measured. And the calibration charts in this case graph the average observed frequency of the simulation, producing an estimate result that falls below the expected percentile value against the expected frequency of each percentile. So the easiest and most intuitive way to explain this is that it compares a statistically ideal distribution of project costs against the distribution of project costs that was produced by each PCEC simulation. So if you were, if you were looking at this and your distribution was perfect, you would expect 50% of the values of the mission to fall at or below the 50th percentile. And this is basically tracking what percent of the simulated data actually does fall below that percent. So the ideal distribution would be this black line that's cutting diagonally through the middle. And as we can see here, the line that most closely resembles the ideal distribution is this green residual correlation matrix. Anything that falls above the black line is overestimating frequently. And this tells us nothing about the degree to which it's overestimating, just the frequency of how much it is overestimating. And anything that falls below the line, so this 0 correlation matrix, is underestimating because it is producing results less frequently than we would ideally expect to find. So as we can see, the green line for the residual correlation matrix is the one that best fits the data and has the least amount of bias. Now, another way we looked at the performance of the model was through the mean percent error. This measures the average strength of model error, and the closer the mean percent error is to 0, the lower the average error in the predictive quality of the model. Positive values indicate that on average, the observed values tend to overestimate the actual value, and negative MPE values indicate that on average, the model tends to underestimate the actual values. In our case, the 0 correlation overestimates around 22% of the time. 0.3 correlation overestimates about 87% of the time. The residual correlation matrix underestimates 0.13% of the time. And then the 1 correlation matrix underestimates 6.24% of the time. So just from the MPE values, our best performer is the residual correlation matrix. But it gets more interesting when you look at the number of missions. So remember, there are 40 missions that were tested in this study. The number of missions that are forecasted within plus or minus 10% and 5% MPE. For 0 correlation, it's 6 and 4. For the 0.3 correlation, it's 4 and 2. So the 0.3 correlation is actually a decrease in effective or in the number of missions from the 0 correlation. But then the residual correlation and even the 1 correlation have far higher scores with 11 missions forecasted within 10%, and 6 and then 8 missions forecasted within 5%. So this indicates that the including the residual correlation matrix is actually improving the model effectiveness significantly. Now, the key difference between this chart and the last chart is that the bias charts show how frequently the costs are being underestimated, and this shows the strength of those over or underestimations. And the key takeaway here is that the correlation of residuals matrix produced the simulation with the lowest error on average. So scope and limitations. This research does not attempt to determine causal factors. There's a lot of different causal factors between subsystems, and it's outside of our scope to really understand their influence. This research does not attempt to produce a correlation matrix that's applicable within any cost model. This was created using the data and the CERs that are specific to NASA's PCEC model. So it's only applicable within PCEC. However, this methodology can be replicated in your own cost estimating models in a similar manner. Then also this research shows how the model is correlated between subsystems according to this methodology, but it does not show what we would define as the ideal correlations. And finally, the point estimates that are associated with the correlation matrix that's explored here are derived from the spacecraft subsystems and support functions. And therefore launch service vehicles, instrument costs, and science costs are not included within these values that are being forecasted. So in conclusion, in all of our methods of looking at the performance of the model, the correlation of residuals methodology has improved the predictive capability of the model. And this can be used in other parametric cost estimating models in the future to improve the accuracy and precision of cost estimates, and hopefully paint a more realistic picture of the possible range of project costs. Thank you.
Any questions for Vicky?
Yeah.
Do you have any feeling for like when you showed the correlation red-green plot? Do you have a feeling for what the noise level is?
Yeah, that's a good question. In terms, I would not necessarily. We've kind of cleaned the data that was used within this plot by taking out anything that is not related to the subsystem or support functions, and that's the most that we've done to try and eliminate noise there.
I had a question on the correlation of residuals. So is that an output of PCEC? Like their CERs, they publish a correlation of residuals from?
So yeah, good question. So PCEC would publish the developers of that would publish the CERs and the residuals and all the documentation associated with that. And I created the correlation of residuals matrix that's shown here. And now this matrix is available on the ONCE database, but it was not originally published with the PCEC version 3.2 or whatever we're on now. Yeah.
You have a pretty broad range in your values. Is this matrix positive semi-definite?
Sorry, can you say that again?
Is your correlation matrix positive semi-definite?
I don't know, to be honest. I would have to look into that. If this is
There's some issues with using, inconsistent correlation matrices. You can get strange values if.
Christian, I think we should maybe talk about that offline. This is just I wouldn't say that this was the consistency was researched entirely of the correlation matrix.
Okay.
Sorry, what were you gonna say?
I was just wondering for the last table that you showed before.
This one?
Yes, there.
Mhm.
I was looking for the residual correlation with the like plus or minus 10%, plus or minus 5%.
Mhm.
Was there a difference in like the mean percent error for like how it performed with like the 10% versus 5%? Like, or I wasn't sure, like I know that was like the average, I think you said between.
Oh, yeah, so, now, do you mean? Let me make sure I understand what you're asking. Is there a difference between like like how much the strength of these like 11 values compared to the other ones, or?
Yeah, so I just feel like the mean percent error in there is like negative like 0.13, but I didn't know maybe it was like above for one and lower. for the
Oh,
other,
yes,
like,
yeah, okay, yes, so, this is mean percent error, so it is not the mean absolute percent error. But the residual correlation matrix was still the best performer with the absolute percent. And I think the absolute percent error value was about 20% for this, so, no problem.
Any other questions? Thank you, Becky.
Thank you.